Hi viewers, welcome to my class on mechanics of materials. In today's class, I'll work out a numerical example to draw the shear force and bending moment diagram. Now let us consider a beam subjected to point loads like this. So there are 3 point loads acting at B, C and D. And direction of support reactions are already shown. Both the ends supports are exerting vertically upward force. Now first step is to find out the reactions at the supports. So to find out the reactions, you can take moment summation with respect to point A, which eliminates RA and you will get RE. So by taking moment summation with respect to point A, these 10, 24 and 34 all are producing clockwise rotation with respect to point A, whereas RE is producing anti-clockwise rotation. So the moment of all these are positive and this is negative moment. So that summation you can take and equate to 0. So the force into distance you should multiply. So 10 into 2 plus 24 into 7 plus 34 into 15, total distance 2 plus 5 plus 8, 15, 34 into 15 minus RE into total distance is 20. So that will give the moment summation with respect to point A, and that you can equate to 0. So the moment summation is 10 into 2 plus 24 into 7 plus 34 into 15 minus RE into 20, that is equal to 0. From that you can solve RE. RE will get us 34.9. So reaction at E is 34.9. Now once you get this support reaction, you can find out the total downward force, that is 10 plus 24 plus 34, 68 is the total downward force. Out of 68, this support is sharing 34.9. So remaining 33.1, that is 68 minus 34.9, remaining load has to be shared by this support. So that will be 33.1 kilonewton. So that way you can calculate RA. Or you can sum up the forces and equate to 0. RA minus 10 minus 24 minus 34 plus RE is equal to 0, and RE is already known, 34.9. So you will get RA as 33.1 kilonewton. So you got the support reactions like this. Now once you get the support reaction, you can calculate the shear force in the various sections and also bending moment at salient points like A, B, C, D, E. But A and E, you know, bending moment is 0. At the extreme ends, bending moment is going to be 0. Now let us take the section AB. In the section AB, only one force is there. Anywhere if you take a section and there is only one force is there, 33.1, and the shear force in the section AB will be 33.1. So shear force anywhere in the section AB is going to be 33.1 kilonewton. Now if you consider a section anywhere between B and C, so there are two forces, 33.1 and this downward negative shear force, so minus 10. So you get 33.1 minus 10 or 23.1. So shear force in the section BC is 33.1 minus 10 or 23.1 kilonewton. Now if you come to the section CD, anywhere between C and D if you take a section, there are three forces to be considered. 33.1 minus 10 minus 24, that will give the shear force in the section CD. So 33.1 minus 10 minus 24, or you get minus 0.9. So in the section CD, the shear force is minus 0.9. Now if you move to the next section, DE, anywhere between D and E, if you take a section, shear force is once again the summation of all these forces by taking upward positive, downward negative. So if you take this section, already we know the summation is minus 0.9 minus 34, that will give minus 34.9 as a shear force in this section. So summation is sum of all the forces, 33.1 minus 10 minus 24 minus 34 minus 34.9. So that is the shear force in this section. Now after getting the shear force, let us calculate the bending moment at salient points. Now bending moment at A is 0 because there is no force here left side to produce bending here. Okay. So 33.1 is acting at A, which will produce 0 bending moment or 0 bending effect with respect to point A. Because 33.1 is the force and its distance is 0 from A. Now at B, if you take, this will produce a bending effect. So this force, I am only taking the left side forces. When you take a point, I am taking only left side forces. The moment produced by this force. So that is 33.1 into 2 clockwise moment. So 66.2, that is the bending moment at B. Okay. So bending moment at A is 0. Bending moment at B is 33.1 into 2, that is 66.2 kilonewton meter. Because it's producing clockwise rotation, the bending moment is positive. Now bending moment at C is going to be 33.1. This is producing a clockwise rotation and the distance is 7. So 33.1 into 7, which is producing a clockwise rotation, so positive, and this is producing an anti-clockwise rotation with respect to C. So 10 into 5, but it is producing a negative moment. So 33.1 into 7 minus 10 into 5, that will be the bending moment at C. So you have to take only left side forces. Don't consider the right side forces. Right side forces, if you consider, you have to consider only those forces, but you will have an opposite sign convention. So bending moment at C, you can calculate like this: 33.1 into 7 clockwise positive, and 10 is producing anti-clockwise moment, and the distance is 5. So minus 10 into 5. So you get 181.7 kilonewton meter. That is bending moment at C. Now let us find out the bending moment at D. Now considering these left side forces, there are 3 forces. 33.1 will produce a moment. This distance is 15. So 33.1 into 15. Okay, clockwise rotation with respect to point D. This 10 will produce a anti-clockwise rotation with respect to this point D. So minus 10 into 13. This distance is 13. And also 24 will produce an anti-clockwise rotation with respect to point D. So minus 24 into 8. So that will be the moment summation. You can also think like this: when you are taking a left side portion, there is an advantage. So while calculating the shear force, upward force is positive, downward force is negative. While calculating bending moment also, left side, I am talking about the left side forces. This upward force will produce a positive bending moment. Downward force will produce a negative bending moment. That way you can consider. It's not a direction of force which is producing a positive bending or negative bending. It is because left side forces we are considering, and with respect to this, downward force is producing negative bending moment and upward force is producing a positive bending moment. So that way upward force will have positive shear force and positive bending moment. Downward force will produce negative shear force and negative bending with respect to any section. So that is applicable only when you consider the left side portion. Okay. So bending moment at D is 33.1 into total distance is 15, and 10 into 13 is anti-clockwise moment. So 24 into minus 24 into 8, so negative 1. So upward positive bending moment, and downward negative bending moment, downward negative bending moment. That way you can treat, and you get 174.5 kilonewton meter. Bending moment at E is going to be 0. If you try to sum up also, you will get 0. 33.1 into 20, the total distance, positive bending, minus 10 into 18, minus 24 into 13, minus 34 into 5, so that will give 0. Okay, so no need of calculating at the extreme ends, especially when point loads are there. Okay, so at the ends, extreme ends, say sometimes if moment is acting, then you will get a bending moment at that point, but extreme left side of that point, the bending moment will be 0. If a couple is acting at that point, then suddenly the bending moment will change at that point from 0 to that value. Okay, so unless couple is acting, you cannot get a bending moment extreme ends. So you understood the bending moment, all the salient points, and the nature of variation is going to be linear variation for bending moment, because point loads are acting, so the variation is also known. Now you can plot the shear force diagram and bending moment diagram. Now let us also calculate bending moment at any section, say at a distance x. The bending moment at a section at a distance x is 33.1 into x clockwise moment. Okay, this 10 will produce an anti-clockwise moment, so minus 10 into the distance is going to be total x minus 2, so minus 10 into x minus 2. This force is 10, the distance is x minus 2, and that will produce an anti-clockwise rotation, so minus 10 into x minus 2. So that is the bending moment at a distance x, 33.1 x minus 10 into x minus 2, or 23.1 x plus 20. So that way you can write down the bending moment equation. Okay, this equation is applicable only for x value changing from 2 to 7. You cannot apply for the section CD or section AB or section DE, because this is particularly written for that section considering these two forces. If you move on to the next section, 3 forces will come, or if you are in the first section, only 1 force is there. So it is applicable only for the section BC. It is also applicable for point B and point C, but not for beyond point C or left side of point B. Okay, so the value of x can change from 2 to 7. So this I have written to understand the variation of bending moment in the portion BC. Similarly, you get in the portion CD or DE, equations can be formed, and you can show that variation is going to be linear variation or straight line variation. We already shown in the previous class the bending moment variation due to point loads is linear, or straight line equation you are getting for that. So it's a straight line equation, and bending moment variation is linear variation. So you can always plot the bending moments when point loads are acting by straight line. You can always plot linear variation for bending moment when point loads are acting. Now you can use this equation to find out the bending moment at point B and C. At point B it is going to be x is 2. When x is 2, you get 46.2 plus 20, or 66.2. So that will be the bending moment at B. When x is 7, that is at C, you will get 181.7. That's same as this. So after writing the bending moment equation, you can calculate the bending moment. So that is not required here. We need only at B, C, D, so which can be easily calculated by taking the moment of the forces. Now we have already obtained the shear force in the various sections and also calculated the bending moment at salient points. Now you can plot the shear force and bending moment diagram. Now we know the shear force is constant in the various sections. On all the sections shear force is constant, and we got the values of shear force. As in the section AB it is 33.1, the section BC is 23.1, in the section CD it is negative minus 0.9, and the section D is minus 34.9. Proportionally you have to show the diagram. Okay, and 34.9 is, even though it's minus, this has to be considered as a maximum shear force. Don't consider the sign into consideration in deciding the maximum shear force. So on this beam, the maximum shear force is induced in the section DE because 34.9 is greater than 33.1. So this is the maximum shear force. Don't consider the sign in deciding the maximum shear force or maximum bending moment. So this part of the beam is subjected to maximum shear force. Now to draw the bending moment, we know at the either end that bending moment is 0, and we have calculated at B, C and D. So you mark those points 66.2, 181.7 and 174.5. Proportionally you can mark 181.7 should be greater than 174.5. Proportionately you mark these points. And nature of variation also, we understood that it's going to be linear variation from 0 to 66.2, and then again from 66.2 to 181.7. This is not a single straight line, you may have different slope, and again 181.7 it is decreasing linearly to 174.5, and again it is decreasing to 0, linear variation again to 0. So this is a bending moment diagram. So at salient points you should mark the bending moment, and all the sections you should mark the shear force also. So this will give the variation of shear force and bending moment along the length of the beam. And from this bending moment diagram you can easily observe that maximum bending moment is at point C, and maximum value is 181.7 kilonewton meter. So that's all for today. Thank you for watching.